Turn the amplifier on. Today, we're not going to try to teach you how to play a guitar. And entertainment is by no means the only use for amplifiers. I would guess that an amplifier of some type will be involved in at least 90% of the equipment that you will work on in electronics. So you see, an amplifier is one of the most important circuits in electronics. It's a device whose output is an enlarged reproduction of an input signal. On the guitar, the vibrations of the strings were enlarged by the amplifier. This is a basic amplifier circuit. By applying a small signal at the input here, we get an enlarged signal in the output here. But how does a circuit such as this amplify? And how much amplification can it provide? There are several methods which could be used to answer these questions. However, in this lesson, we'll concentrate on the method which uses this graph, the characteristic curve of a transistor. On this graph, we'll plot a line of voltage-current relationships which will take into consideration the collector load resistor of the amplifier circuit. This line is known as a load line. You'll find that a load line can be constructed simply by knowing the size of the load resistance, the amount of VCC, and Ohm's law. Then, using this circuit, we'll compare the values on the chart to the actual base current, collector current, and collector to emitter voltage of the circuit. Briefly, here are the steps we'll go through to demonstrate how an amplifier works and how much gain it provides. We'll construct a load line, select a point of operation on this load line, apply an input signal, plot current and voltage changes caused by this input signal on the load line. Then, using the current and voltage changes, we'll compute gain. We'll also change the size of the collector load resistance and see what happens to current and voltage gain. To illustrate a load line, we'll use a simple DC circuit with two resistors. One resistor is variable from 0 ohms or short to an open, and the other resistor has a fixed value. The voltmeter measures the voltage across the variable resistor, and the ammeter measures total current in the circuit. As the resistance is varied, we'll put current and voltage on a graph. With the resistor adjusted to 0 ohms at position A, the current is maximum and the voltage across the variable resistor is 0. This is one of the limits of the circuit. On the graph, voltage is at 0, current is at maximum. As the resistance is varied to an open at position D, the voltage increases to maximum and the current decreases to 0. This is represented on the graph as point D here. The maximum voltage we can have is the applied voltage. If the arm is moved from position A to position B to position C to position D in steps, a series of points would be generated that would be on a straight line between positions A and B, between positions A and D. Using the simple resistive circuit as an example, we can describe a basic load line. A load line is a line that represents all possible current and voltage values in a circuit. Point D is determined by the applied voltage, and point A is determined by the load resistor. The points in between A and D are controlled by the variable resistor. Since a transistor acts like a variable resistor, we can use the idea of a variable resistance to describe the basic load line in a transistor circuit. Depending on the amount of base current, a transistor can vary from almost a short to practically an open. With this in mind, let's connect a transistor in series with a resistor known as a collector load resistor, or RL, and a power source, VCC. First, we need to create the two extremes of transistor operation. To show the circuit conditions when the transistor is shorted out, let's put a short across the transistor like this. Collector to emitter voltage goes to 0 and collector current rises to 7.5 milliamps. This is the maximum current that will flow in this circuit. On the graph, 7.5 milliamps and 0 volts collector to emitter voltage falls right here. This is a point representing one of the limits of the circuit. Now, let's remove the short. And to show the circuit conditions when the transistor is not conducting, we'll remove the transistor from the circuit. Now we have an open, and the collector to emitter voltage is 15 volts, while collector current is 0 milliamps. This point of 15 volts collector to emitter voltage and 0 milliamps of collector current is right here on the graph. 15 volts is the maximum voltage in the circuit. By connecting these 2 points on the graph with a straight line, we have the load line for this transistor amplifier. Having constructed the load line, the next thing we need is that point on the load line that represents the circuit conditions prior to an input signal. This is called an operating point. The transistor's base current is going to determine the operating point. So let's first identify the base current path. Base current has a path from VCC through this variable resistor to a base current meter to a base to emitter resistance of 4K ohm to ground. The base current meter is reading 50 microamps. On this graph, 50 microamps intersects the load line here. This is the operating point for this circuit. With a base current of 50 microamps, the collector to emitter voltmeter reads 9.8 volts, and the collector current meter reads 2.6 milliamps. This is the current and voltage relationship of the transistor at the operating point. The actual circuit agrees with the curved values. With the load line drawn and the operating point determined, we are ready to apply an input. The input adds to and subtracts from the base current. Remember, the operating point is where the selected base current line intersects the load line. The load line is a line drawn between the two operating limits of the circuit. The two limits are when the transistor is shorted out of the circuit and when the transistor is removed or acted as an open. As the input is applied and base current changes, let's observe what happens to collector current and collector to emitter voltage. As base current increases from 50 microamps to 75 microamps, collector to emitter voltage decreases to 7 volts, and collector current increases to 4 milliamps. On the load line, that is right here where the 75 microamp base current line intersects the load line. Then as base current decreases to 25 microamps, collector to emitter voltage increases to 12 volts, and collector current decreases to 1.5 milliamps. Movement is down the load line to here, where the 25 microamp base current line intersects the load line. From the graph, we have indications that a base current change of 50 microamps peak to peak causes a collector current change from 1.5 milliamps to 4 milliamps, or a total current change of 2.5 milliamps peak to peak. Well, with a 50 microamp change in the input and a 2.5 milliamp change in the output, What's the current gain? All we have to do is divide the change in the input current into the change in the output current. The current gain is 50. At the same time current changed, the graph indicates a collector voltage change from 7 volts to 12 volts, or a total of 5 volts peak to peak. Okay, we have a 5 volt peak to peak change in the output, but what was the input voltage change? Remember we said earlier the base to emitter resistance was 4K ohm. Well, with a 4K ohm of resistance and 50 microamps of base current, according to Ohm's law, the input voltage change must be 0.2 volts peak to peak. What's the voltage gain? To find the voltage gain, we divide the output voltage change by the input voltage change. The voltage gain is 25. While watching the current meters, both base and collector, we can observe the current gain, but we cannot readily see the voltage gain. What we can do is apply an AC signal to the circuit and observe both the input and output signals on this oscilloscope. The upper trace is connected to the input and is now reading 0.2 volts peak to peak. The lower trace is connected to the output and is now reading 5 volts peak to peak. So this way we can actually observe a wave shape that represents the amplified voltage. To summarize, we have gain in this amplifier because a small input current change causes a large output change. But to see where this amplification occurred, we need a graph of characteristic curves for this circuit configuration on which to construct a load line. To get a load line, we created the two limits of the transistor operation within a circuit. To do this, we first shorted out the transistor and then opened the transistor. We plotted the current and voltage points that resulted from the short and open on a characteristic curve chart and drew a line between these 2 points. After drawing a line known as the load line, we found that the operating point was located where the base current line intersected the load line. We observed the changes along the load line that were caused by the very small input signal. To find out how much variation occurred in the output, we went from the lower and upper intersection on the load line across to the current axis. This told us the amount of change in the output. We also traced from these 2 intersections on the load line down to the voltage axis on the curve. This indicated the amount of voltage change in the output. Comparing the input voltage to the output voltage, we get an indication of the amount of amplification that the circuit is producing. Having constructed and used the load line to discuss how the circuit amplifies, let's change the size of the collector load resistor and notice what happens to the load line. We will also see what happens to gain while changing the load resistor. Keeping the same VCC and input signal and using the load line we just drew for reference, we will change only the load resistor. If we keep the same applied voltage of 15 volts and increase the load resistor to 4K ohm, the current represented by point A is decreased as shown by the solid line. Comparing the new change in collector voltage to the old change, the swing in collector or output voltage has increased. Making the same comparison with current changes, we see that the new current produced by the new load line has decreased in comparison with the current produced by the load line of the smaller resistor. From this, we can conclude several things. First, that the load line drops with an increase in collector load resistor size. Also, that as the collector load resistor size increases, voltage gain increases and current gain decreases. We began with a small resistor and increased it. The load line dropped to here. We had a decrease in current gain and an increase in voltage gain. If we started here with a large resistor, say 4K ohm, and decreased the resistor to 2K ohm, the opposite would have happened. Current gain would have gone up and voltage gain down. An important conclusion is that a current amplifier would have a relatively small collector load resistor, and a voltage amplifier would have a relatively large collector load resistor. Okay, that's what it should do. Will a trainer support this theory? Let's see. Changing the collector load from 2K ohm to 4K ohm should cause the output voltage wave shape here on the lower trace to increase. As the resistor is changed from 2K to 4K, the output does increase. The actual circuit proves the conclusion that we made from the graph. As we increase the collector load resistor, the voltage gain increased. A larger resistor produces a high voltage gain. Likewise, a small collector load resistor produces a high current gain. In conclusion, we can say gain is obtained in an amplifier because a transistor has the ability to convert a small input signal into a large output signal. Amplifiers are so important that they are found in almost all electronic equipment, including televisions, radios, electric guitars, hi-fis, stereos, missiles, radars,